Okay, lab partner, here we are back up front, and we can all see that we have now filled in. I'm sure you have we got out of the way here. The trials 1, 2, 3, 4, 5, and 6. I put a line here because 6 is special, again, like you kids, special, that you weren't measuring. We were trying to get not the time, but we were trying to get a length out of that. So it was just a little bit different in that trial. And that's why I put a little star next to it here on the lab handout. And there's a star here for calculations down here because you're dealing with number 6, which is a different calculation than trials 1 through 5. So let's go through that quickly. So I'm going to get rid of this. So hopefully at this point you have this all filled out. You have the masses we used. We have the length that we use and the times. Now for trial 6, we had the time. So you're going to put the time in there. 19.72? I don't remember anymore, but hopefully you do. And if you timed it, okay, maybe you got a different time, or maybe it's somewhere in the ballpark, hopefully, but use your time. So the time it took to go back and forth 20 times, put that here, it was close to 20 as we could get, because that's what we want. It'll give us that length that we're looking for in this one. So trial 6 is a little bit different. We're going to figure out the length here. That gave us the time of around 20 seconds. Here we knew the length, we measured those out, and we got the time, so it's kind of reversed for trials 1 through 5 and then trial 6. Okay, we need the pendulum equation. So let's get rid of this. We're good here. You have your data. All righty. So now we can go ahead and look at that pendulum equation. And I know you've all watched the videos. Yes, you have. You watched the videos that I put in there from College Board. You'd better, because, oh, geez. Looking good now. Look at, oh, wait, came up button. Looking good, okay. Yeah, you watch those videos, and it talks about time period with springs and in pendulums. Doggone it, you'd better go watch those because you need to watch them. So here is your equation for pendulum. It is T is equal to, now that's time period. Okay, the time period is how long it takes to go back and forth, back to your starting position. Okay, out, back with me. All right, time period is 2 pi. If I had a choice of 2 pi, I'd go with apple and blueberry. That's what I'm talking about. Everyone loves pie. SpongeBob, Kevin, we love you, Kevin. That was the episode. All right, and so you get pie. You made a pie, and the jellyfish went after it. I mean, you know what I'm talking about. Square root of L over G. All right, now here's our equation. Just by looking at the equation, we should know, and after watching the qualitative video, we should know, and after getting our data, we should know the mass doesn't seem, hopefully our data verified that. I don't know what the times are. You do. You timed it. Okay, hopefully those times were not much different. You know, there's some of this, and some of you are terrible at starting and stopping a stopwatch. So there could be some error there. Of course, the lengths weren't exactly the same. There's going to be a little bit of error. But we're looking at, were the times within a second of each other? You know, within a second, that'd be pretty good. And that means they're basically the same. So when it comes to the mass, we can say it's not in the equation. It's not in the equation. It's not involved. It doesn't matter. Mass don't matter. The length of the equation matters. We know that. We vary the length, and we saw when there was a short pendulum, long pendulum. All right, well, why is that? Because the longer the pendulum, okay, it's on the top of the equation here. Well, it's a square root direct relationship, but it's still direct in terms of you increase this, you increase this. All right, so that mattered. Length of the pendulum. And here's little g. Little g is, Earth gravity 9.8. We're using 9.8. The pendulum is being pulled down by gravity, and it's stopped by gravity, pulled down and stop, pulled down and stop. And if we're on the moon, it's going to be a different rate. You can actually use pendulums as timepieces. You can use them to calculate g on a different planet. As a matter of fact, that's one of my questions. Well, my question has to do with how could I use a pendulum to determine my altitude on Earth, above the Earth? How could you do that? I'm not going to answer that question. That's for you to answer. That's why it's a question, okay? All right, I'm not doing the lab. You are. But it is one of my questions, and you can use this for altitude or to determine g on a different planet. You can take a little pendulum to Mars and let it go and do a time period and a length and determine gravitation on Mars. Who wouldn't want to do that? Pretty fun. Pretty fun. So here's our equation. Now we're setting this up. What we're going to do is we're using the pendulum to go. You can actually use it for a number of different things. You can use it for potential and kinetic energy. And in this unit, we'll talk about that. In one of the videos is about oscillatory motion and energy. Potential, kinetic, potential, kinetic, potential, kinetic, potential, kinetic, potential, kinetic, potential. You get it. Until you have friction, and of course, eventually it'll slow down and stop. But potential energies and kinetic energy, pendulums are great for that. They're great if you wanted to graph a pendulum. You could graph it, and you get the low, high, low, high, low, high, low, low, high, low. You're getting a sine wave out of that bad, Larry, aren't you? And now we also can use it. We're going to use it in this lab to solve for G. We know what G is. I know, but let's just go ahead and use it. If the pendulum equation works, then we can use it to solve for G. And that's what you're going to be calculating here. Show the calculations 1 through 5. Then I need you to complete the calculation table. So here's a calculation table. I want you to fill in this table. Fill it in. Do it. Show your calculations of how you get these for trials 1, 2, 3, 4, 5, 6. Time period. Time period is the amount of time to go back and forth once. Now, we did it 20 times. So, how do I get time period? Well, time period, as we all should know. Okay, we'll get rid of this for a second here, the pendulum equation. You're going to use this equation to solve for little g, but you need a time period. So the time period is the inverse of the frequency. Time period is inverse of the frequency. And therefore, frequency is inverse of the time period. And so what we have to know is, the time period, how long it takes to go back and forth once. But we didn't get a frequency on this. We didn't get the amount of times per second, although we could do that. We could. But just know that these two are inverse of another. But another way to get our time period, if we knew the frequency, of course we'd have to know the time. But what we could also do is take the amount of seconds it took to go 20 times. So let's say it takes, I don't know the times, maybe 23 seconds to go back and forth 20 times. I don't know, trial 1, that was the long pendulum. It was like, I don't know what the time was on that. But maybe, I don't know, I'm just making this number up. I'm just making it up. Okay, maybe it was 23 seconds. It was 23 seconds to go back and forth 20 times, then what is the time period? How long does it take to go by once? Back and forth once. So 23 divided by 20. So take the time, the total time, and divide it. In fact, no, I didn't put it on here, so I'll write it down for you. So take total time, back and forth, the amount of time, and you have those written down, and divide it by 20. That'll give you the time period. That'll give you T for each of the first 5 trials. Now I say 5 trials because we did 6, right? Well, yeah, we did 6. What about that? That one we knew the time, so we weren't trying to do a time. Okay, I'll get to that in a second. Okay, I'll get that. Let's do 1 through 5. So trials 1 through 5, so time period. So take your total time per trial divided by 20, and you get that value. I know the last couple of trials seem to be pretty quick, so they're not going to be like 23 seconds. There actually be a time period should be less than a second for trials 2 and 3. It might be greater than for trial 1. I just remember it took a long time, but I don't know if it took more than 20 seconds or not. So get that time period by dividing your time by 20. And also remember that this is an inverse relationship. Okay. So if we do get that time period, then we can actually get the frequency. We can then take that time period and divide it by the frequency. But let's get that time period, divide by 20, write it down. Once we've got that, now we can calculate little g, because let's go back to our equation. The equation is 2 pi square root of L over G. Now, you can see that, right? Yeah, okay, it's kind of, well, hopefully you can. And this length, we know. I told you, we measured it. I remember the last one because I had to keep repeating.